All right. For question number 1, your marks distribution is going to go like this. The first thing we always do is we write down our givens. So if they have givens written down, okay, they can have a mark for that. Okay, the givens were that the bus traveled 2,500 meters north in a time of 75 seconds, okay, and then it turned around and traveled 18 meters per second south, okay, so that's a given right there for 55 seconds, right, so they should have had those things there. Now, for part A, we want to calculate the total distance traveled by the bus. We know how far it went in part 1 already, but we do not know from the givens, which is just v and t, how far it went in part 2. But because we have velocity and time, we can find out how far it went by doing this operation right here. So we manipulate v equals d over t for d. So v times t is 18 multiplied by 55, so 18 meters per second south multiplied by 55 seconds gives us 990 meters south. So if they have that operation, give them a mark. Okay? They do not actually have to have the 990 meters. If they made a mistake on their calculator but they showed this step, you can give them a mark. It's a method mark. Okay? Now that I have the distance traveled in part 2, and I know how far it went in part 1, can I calculate the total distance traveled? Okay, that's our next mark. Right? So the solution for part A is right here. We have to add those two numbers together. We add them together because distance is scalar or vector? Scalar. Doesn't matter that one was south and one was north. We're just looking for how far did this thing go. All right? So they actually do have to get 3,490 meters in order to get that mark. Okay? So a mark for 3,490 meters. They cannot have a direction on that. If they did put a direction on that, it is unfortunately wrong. It must also have units. If there's no m beside that, it is also wrong. Okay? They must have units on their answers. Okay, in part B, I want to find the average velocity of the bus. What two things do I need to get average velocity? I need two totals. What are they? Total displacement and total time. All right, so total time, 75 plus 55. Right, so that's a fairly easy operation. Total displacement, 2,500 meters north plus 990 meters south. Since they're opposite in direction, I'm actually adding a negative number, or I'm just subtracting, whichever way, okay, is fine. So here's your next couple of marks. They get a mark for showing this, okay, the 2,500 minus 990. Okay, if they went straight to this, that's fine as well. If they have either what I have circled here in red or what I've hash marked circled here, okay, that's fine. They showed that operation in that they knew they had to subtract these numbers and add the numbers on the bottom. All right, so we've got our total displacement over our total time, and then, okay, we have our final answer, 11.6 meters per second, and we must have the north on there as we did solve for a vector quantity. So they must have the meters per second, and they must have the north. All right. If they had a couple of extra decimals on there, that's fine. If they just rounded differently, okay. All right. So that one, guys, okay, is out of 5 marks. So you got 1 mark for your givens, 1 mark for this. Okay. You got 1 mark for the total distance traveled, 1 mark for your calculations here, and 1 mark for your final answer for a total of 5. Questions on number 1? Okay. Question number 2, in running a line drill, in basketball we call that a suicide. I know that's probably not a politically correct thing to describe it as, but that's what we call it because afterwards, oh my God, you feel awful. Okay, so you run to the foul line and back, the center line back, the foul line back, the opposite baseline and back. Okay, at least on our team you got to do that in under 27 seconds. All right, so it's a lot of running. It's back and forth. But the really unfortunate part of that is from a physics perspective, when you're done the drill, where are you? Nowhere. Yeah, you're right back where you started, on the baseline. Okay, so in running this line drill, we run forward 15 meters at 10 meters per second, then backwards 10 meters for 1.1 seconds, and then forward another 15 meters for 1.6 seconds. What's the average speed of the basketball player? All right, the question gives me forward, backward, but then asks me for speed. Does forward, backward matter anymore? It doesn't. Okay, so we can forget about forward and backward. Direction is not going to matter for what I have to solve. Speed is scalar. So 1 mark for givens. They have, okay, the 15 meters written down, okay, and the 10 meters per second written down, okay, and then, okay, basically all these other givens here. All right, we got to have all of those. That's 1 mark. If I want to find average speed, again, I need 2 totals. What are they? I need time and distance totals. All right, this time I need distance because I'm looking for a scalar quantity. All right, they told me in the first one that I go 15 meters. They told me in the second one I go 10 meters. And, all right, so I got total distance already. I got the D for every single one of those sections, so I don't have to do any of that. The thing I don't have is time for all 3 parts. I was given D and V for the first one. So I've got to do a little calculation here in order to get the time it took to run part 1. All right, so give them a mark if they had T equals D over V, okay, or if they had, instead, they plugged in the numbers and they went 15 over 10, okay, I would accept that as well. All right, so 1 mark for that and 1 mark for the answer, 1.5 seconds. Okay, their next mark is going to be, all right, so we're up to 3 marks now. Okay, so their next mark is going to be for showing the totals here. So 15 plus 10 plus 15 for a total of 40 over 1.5 plus 1.1 plus 1.6. So if they had either this or this, okay, whichever one, give them a mark. And then our last mark is for the final answer, 9.52 meters per second. Total distance over total time. No direction on that. They must have the units on that, okay, in order to get those marks. Quiz is out of 10. Please give them a mark out of 10. Let them see it. Put it in the box. Any questions? All right, let's get her done. Okay. Most important tool for physics. Graphs, not calculator, okay? Calculator would probably be the second most important tool. Graphs are the most important tool. Here's why. A graph very quickly allows us to visually discern the relationship between 2 things. All right? If I look at a graph and I see that it goes like this, okay? I right away know that as time increases, this object goes faster, okay? It tells me that right away. I know that the longer this thing goes, the faster it's going to be going. I can see that visually right away. That's an important tool, okay? It tells me the relationship between 2 variables that I might be studying, okay, or measuring or something like that. All right? The other reason it's important is sometimes it actually allows us to calculate a numerical relationship between those 2 things, okay? This line here, right, could tell me the rate at which this object is accelerating, right? Which is essentially how fast it's going faster, right? The steeper that line is, the faster it's accelerating, right? If that line, instead of being angled like that, looked like this, what does that tell me? Right, it's not increasing speed over time. In fact, it's traveling a constant speed, okay? What does that one tell me? It's not moving because the line goes at 0 all the way along, okay? So that object's not going anywhere, right? Similarly, okay, if I had, or not similarly, but as a, what's that object doing? It's slowing down, yeah, or accelerating backwards. They're kind of the same thing. We'll get to that when we talk about acceleration. But in order to slow down, you actually have to accelerate backwards. Again, this is a total cultural thing for us as North Americans. We do not get our heads around that very well because we don't think our brakes in our car make us accelerate backwards, even though they do. The only thing is they'll never make you move backwards, right? Everyone follow me on that? But think about if you're in a boat. How do you slow a boat down? Okay, you can turn the speed down, but what if you wanted to like stop the boat real fast? You reverse the motor. Okay, make the motor go the other way, make the propeller go the other way. Okay, then it's trying to pull you, right? Okay, that's how big ships, okay, like big naval vessels and stuff, that's how they'll slow down and stop. They actually make the screws, that's what they call them, the big propellers on the bottom. Okay, they make them turn the other way. That way it pulls back and stops the ship. Right? So to stop or to slow down, they actually accelerate backwards. Right? Everyone follow me on that? It's weird. We'll talk about when we get to acceleration. Okay, but you can see here, okay, just looking at those graphs right away, we were able to know here's what's going on. Right? And we can calculate mathematical relationships from those graphs. Okay? If instead of speed and time, this was, let's say, price of oil and time. Okay? We would be able to figure out just how much the price of oil was going down every day. Okay? Because, yeah, this last little while, that's been a really steep downward line. Okay? Hopefully that's going to be a steep upward line again real soon. All right? But it can tell us, essentially, how quickly something is changing. All right? And that's an important thing to know on a graph. Everyone follow? Now, here's the good news. We're only going to make graphs by hand basically today. All right? We're going to make a couple just so that we have the general mechanics of how a graph works. And after that, we're always going to make our graphs electronically because they're better. All right? The computer draws a graph way better than we do, and it does it way faster. All we got to do is plug in the numbers. All right? So we'll be using Google Sheets. In fact, tomorrow we'll have the Chromebooks and we'll be practicing. Okay, I'll show you how to do a best fit line and all that kind of stuff on Google Sheets, get the slope and all that kind of stuff. Okay, how many people have heard that term before? Slope. Good. I love teaching science second semester, okay? Because you all have taken math by now, and you've all done graphing, okay? And so this is so much easier second semester than it is first semester when half the class looks at me and goes, "Is slope a Greek word?" Okay? No. Okay, it's not. All right. So obviously, the first thing to plotting a line graph is to get a piece of paper, a ruler, and a pencil. Again, we're probably not going to be building too many by hand, so that's going to be less important. Okay. And then you draw your two axes. The things we need to remember here, okay, is that the vertical axis is the y, and the horizontal axis is the x. Okay, that's important when we start using this formula. Y equals mx plus b. We have to understand that y values come from the vertical axis and x values come from the horizontal axis. Okay. Another thing we need to know, the manipulated variable is always on the horizontal axis, okay, and the responding variable is always on the vertical axis. Right? It is crucial that we know that, because what we want to see is the change in the responding variable as a function of our manipulated variable. Okay? Everyone follow me there? All right? Most of the time, and by most of the time, I mean essentially every time. Okay? Time is a variable. Time will be the manipulated variable. Right? Now, sometimes people are like, I can manipulate time? Cool. I'm going back in time. No, you're not. Okay? I don't mean you're manipulating time and that you're making it run faster or slower or backwards or sideways. Okay? I'm just saying that we control, when time is a manipulated variable, we determine how long the experiment will run for. Okay? In that way, we're manipulating the time. We're only allowing the experiment to run for 10 seconds or 10 hours or a day. Everyone follow me there? Okay? That's how time becomes a manipulated variable. But any time, at least in this course, time is one of the variables. It's going to go on the x-axis. It's always going to be the manipulated variable for us. All right, the other thing is when you're building a graph, either by hand or electronically, you must put labels on the axes. Otherwise, it's really hard to tell what a graph is telling you. Okay? If you don't know what's on each axis, the numbers are really kind of meaningless. All you know is that when one thing goes up, so does the other. But you have no idea what those things are. Okay? They could be, the number of people who purchase umbrellas on a rainy day versus on a sunny day. Okay, or something. But you wouldn't know because there's no units and no labels, right, on the axis, so it becomes kind of useless. Okay, and the other thing is that yes, you always need to have units. Okay, so I know it seems like we're underlining everything, but for the first little while, we are. Okay, always include units. Because looking at this graph, It's time in seconds and speed in kilometers per hour. But this, if this graph looked like this, like we were saying at the beginning, all right, I might say, wow, it changes its kilometers per hour in just a few seconds. But if there's no units on here, and it was actually measured in days, is that acceleration quite a bit different? Yes. Okay? If it took you 5 days to reach 100 kilometers per hour, that's quite a different rate of acceleration than doing it in 5 seconds. Okay? Everyone follow me there? Okay, and you obviously need a title, because quick reference, right? You want to look at a graph and go, oh, that's telling me about this. I don't need to know that. Switch to the next page. Okay? Or, oh, that's exactly what I was looking for. I better stay here and have a closer look at this graph. Okay? So they always need to have a title. Now, choosing a scale. When you're building a graph by hand, choosing a scale is probably the thing people screw up the most. When we do them electronically, the computer picks the scale for us, and it's really nice. All right? But we want to make sure that we know how to do it. Okay? When you're picking a scale, what we mean by that is picking a number that each square represents that will make all of your numbers fit on the graph. Okay? How many of you had this problem before? You're making a graph, you're drawing along, you're like, okay, I'm going to make every box worth 2, 4, 6, 8, 10. Uh-oh. I was supposed to get to 15. Oh, well. What's wrong with that graph? It's not uniform. That last square represents 5. Every other one represented 2. Okay? It kind of screws up my graph a little bit if my scale isn't true all the way along. Every box has got to be worth the same amount. Okay? In order to get that right, what we do is we take the biggest number we have to graph and we divide it by the number of squares we have. And then we always get the right number. Okay? Everyone follow me on that one. So it's pretty straightforward. The only trick is rounding. Some people mess this up. Okay, so down here in number 6 here, they're telling us, okay, let's say you've got a scale that starts at 0, ends at 700, and you got 30 squares to fit it all in. So you go 700 over 30, and you get 23.3. According to what you've learned your whole life, rounding rules say you should round that to 23. Here's the problem. If you round that to 23, are all your numbers going to fit on your graph? No, because each line was supposed to be worth 23.3. So for the first 3/4 of your graph, it's going to look like everything is hunky-dory. All right? And then you're going to get to the last line and realize you're short 2 squares. Okay? So we don't want that to happen. Whenever we get a decimal, we round up. Okay? And would you really realistically graph every square worth 23? Or 24? Are those easy numbers to count by? No. So you want to pick a nearby convenient number. All right? If I got a decimal that was like 4.15, I would conveniently round to 5 because it's really easy to count by 5s. Okay? For this number, it would be really easy to round to 25 and make every line worth 25. All right? That's an easy number to count by. Everything's going to fit, and I'm going to use up still pretty much the whole graph. All right? What you don't want to do is say, oh, it was, the number I got was 6.2, so I'm going to round to 10. Those numbers aren't really close, okay? And if I make every line worth 10, I'm only going to use up about a little more than half of my graph, okay? So I'll have this full scale. So I'll have this graph here, goes all the way out to there, but my data will only go about that far. Did it really make effective use of my graph then? No. Okay, so you want to pick a scale that uses up as much of the graph as you can, okay, but still is a convenient number to count by. Okay, that sort of makes sense to everybody. All right, so that's how you do that part there. Okay, when you're filling it in by hand, and again, we're not going to do much of this by hand, okay, you could write every single number, okay, so 0, 25, 50, 75, 100, but if your writing's like me, that's not going to be a recipe for a legible graph, okay? Because they're going to be really crowded and messy, and it's just not going to look right. So people will still know, looking at this scale, that every line is worth 25. Would you agree? Yeah, because every second line was labeled as 50, right? So that's a much easier way to make the scale and make it legible, okay? Things like that, all right? Okay, when you're actually plotting a graph by hand, you should do it in pencil. Why? right? So if you mess up, you can erase it, okay? I have seen so many people on tests in previous years, okay, when I used to make them actually like construct a graph on a test, they would do it in pen, and then they'd come up to me, Mr. Coder, can I have another test? I'm like, why? So I did my graph in pen. Yeah, you realize that that's costing you a mark now, right? Okay, because the instructions say to do it in pencil. Yeah, so you always want to do it in pencil if you're constructing one by hand. Again, we're not going to make many by hand. All right, other little things to remember. Okay, the point 0, 0 is the origin. Okay, so if you ever hear me use that term, the origin, I mean the point 0, 0 on the graph. All right, other terminology, grid lines. Okay, grid lines are the lines that make the graph paper look the way it does. And in Google Sheets, we can choose how many grid lines we get, which is nice because sometimes you want lots and sometimes you don't want very many. Okay, it all depends on how accurate your measurements are. Okay, that is, you know, did you measure to the nearest millimeter or did you measure to the nearest meter? All right, if you measure to the nearest meter, you don't need millimeter grid lines on your graph. Okay, it just makes it look crowded and busy. All right, so you can choose how many grid lines you want, okay, or how often you want them, and I'll show you how to do that tomorrow. All right, a gridline intersection is a point where grid lines cross each other. These are good, okay, for this reason. They're useful for this reason. I can go straight across to each axis and know the exact value at that particular point. All right, so what I mean by that is, okay, if for this particular grid intersection, let's say right here, okay, I know, wow, that is so not where my pen is. Now I got to guesstimate it. That's still not there. Okay, so I can go across to the y-axis and go, all right, that point's value, y value, is 25, and I can go straight down to the x-axis, okay, and know that that x value is exactly 30 or whatever it is, right? Because I can follow it straight down. If it's anywhere in between grid lines, then I have to estimate, and that's not as accurate. So grid lines are convenient in that way. Okay, x-axis, the horizontal axis, y-axis is the vertical axis. Okay, best fit line. How many people have heard that term before? Okay, line of best fit. How about that? What are you doing in math? You can't use y equals mx plus b without a best fit line. Do they call it something else? Oh my gosh. Left hand and right hand, I got to talk here. Okay. Line of best fit is the line you draw, or that your calculator draws in some cases, okay, that represents the trend of your points. Okay? If your points are going upwards, your line of best fit goes upwards. Okay? So it takes an average of the plotted points. It's straight, not curved, okay, and goes through as many points as possible. That part, I don't like that part. Okay? A best fit line, sometimes a really good one, won't get any points on it. It all depends on the distribution of your points. Okay? But I have way too many people who, when they draw a best fit line by hand, are all about, ooh, connect the dots. Yay, I got 5 dots. No, and then their line is like nowhere close. All right? This isn't like grade 4 anymore. Connecting the dots is not going to make a pretty picture of something. All right, we want to just draw a best fit line that follows the trend of our points. Okay, and you can see here on this graph that there's really only one point that ended up on the best fit line. Right? And that's okay. This line still follows what the points did. Okay, it follows their general trend. All right, now to calculate the slope of a line. All right. How many of you have done that in math already, calculating slope? Okay, in math, did you use this, or did you use second one? Okay, I'm going to show you how to use both. Okay, they're actually the same formula, believe it or not. Okay, they're actually the same formula, but okay, I'll show you why here in just a minute. All right, so you guys have done rise over run. Okay, all right, so we'll look at that first. Okay, you guys obviously have done that already. So the big thing here is that the values y2, y1, x2, and x1, where do they have to be? Okay, not just on the graph, but on the on the best fit line. Okay? I can't calculate the slope of a line using points that aren't on it. Okay? That would be like asking somebody what pomegranate tastes like after they ate a pear. Okay? They ate a pear, not a pomegranate. They don't know what a pomegranate tastes like. Okay? They just ate a pear. So I got to use points that are on the line because they can tell me about the line. Points that aren't on the line can't. I'll show you why. Okay, so let's say I've got this graph right here. Here's my best fit line. Here's some points that I plotted. Okay? I'm going to calculate the slope of my line using this point and this point. If I connect those two dots with a line, does it have the same slope as my best fit line? That is why I cannot use points that are not on the line to calculate the slope of a line. They won't give me the right slope. Agreed? I can only use points that are on the line to get the slope of the line. So what if none of my plotted points ended up on the line? Well, actually, it's not rough. It's okay. Because on a real graph, there's a whole bunch of grid lines on here. Agreed? All right, so let's say that on my graph, my best fit line happened to go through a grid intersection right there and a grid intersection right here. Those are imaginary grid sections, but let's just say that that happened. Okay, so if I go straight across from here, I'll know what the y value is. And same thing up here. If I go straight across to here, I'll know this y value. Everyone follow? All right, so this is y2 and this is y1. How do I know which one's 1 and 2? Did y1 happen first? That's how I know. Okay? This right here is point number 1, and this is point number 2, because this one happened first according to the x-axis. It's always according to the x-axis which one happened first. All right? So if I go straight down to here, this will be x1, and this will be x2. Then I can do rise over run. Okay, and I can do y2 minus y1 over x2 minus x1. Everybody okay with that? All right, how many of you have used y equals mx plus b already in math? Okay, good. Here's how y equals mx plus b and rise over run are the same formula. Okay, on a graph, if I have a best fit line that looks like this, okay, everyone with me so far? Okay. Let's say I'm going to use a point. Wow, that's really annoying. I'm going to have to recalibrate here. Okay, so I'm using this point that's on my line. Really it is. Okay, it has a y value, and it has an x value. What do we call this spot? The Y-intercept. And we use what variable to represent it? B. Okay, the y-intercept in y equals mx plus b is b. All right, everyone follow me. What is m? The slope, right? Okay, so y equals mx plus b. All right, I want to find the slope of the line, which is m. So if we concentrate and think about our rules of algebra, okay, it said if I want to move something, I do the opposite. What I do to one side, I do to the other, and move what's not attached first. Okay, I want to get m by itself. What's not attached to m right now? B. All right, I'm adding b, so I should. All right, so I've got y minus b equals m times x. Everyone all right with that? How do I get x over to the other side? Divide. Okay, so the slope, which you guys said is rise over run, is equal to y minus b over x. So let's look at this. On this graph, is y minus b really just y2 minus y1? And what's the value of x right here? 0. So is that really just x2 minus x1? It is. It's the same formula. So you can use either one, because they're really the same. Okay, when you manipulate y equals mx plus b for m, you're really just doing rise over run. Okay, it's just a little bit easier because you don't actually have to find 2 points. Okay, you use the y-intercept as 1 point, then you only have to find 1 point on the graph. Okay, because b is always going to be there. All right, everybody follow me there? Okay, either way will work, whichever way you're comfortable with, but I'm showing you, okay, when you get to grade 11, you'll have to use this a little bit more. Okay, all right. So you may have also been taught the triangle method, which is again just another way of doing y2 minus y1 over x2 minus x1. Okay, the danger of the triangle method, and the reason I don't like it very much, is people tend to, instead of actually going, 4,000 minus 1,000, they go 1, 2, 3, 4. And they count how tall the triangle is, and then they go, and the triangle's 1, 2, 3 wide, and then they go 4 over 3. Is that your real slope? It's not, because your slope is in thousands over hours. Like, it's just, people do that and they make mistakes. So I don't really teach the triangle method very much because I just find people mess it up too much. Okay, so y2 minus y1 over x2 minus x1, I'm good with that. Y equals mx plus b, I'm even better with that. Okay, whichever way you want to use is fine. Okay, all right. So let's try a couple here. I'm going to give you guys a sheet of graph paper. Okay, and I want you guys to plot this data. Now, when we look at this data, okay, we're looking at the effect of diameter on circumference. Which one's the manipulated variable? Diameter. Okay, diameter is the manipulated variable, so it goes on which axis? The horizontal axis. It goes on the x-axis. Circumference is going to go on the y-axis. Okay? All right, so we'll do this one together. So you can use the front side of this graph. We'll use both sides, even though there isn't actually lines on both sides. We'll use both sides here anyway. Okay, follow along with me here, guys. Do what I'm doing on your sheet, okay? So you can follow along with the construction of this graph. All right, I need to get diameter. I need to put diameter on the x-axis, okay? The biggest number I have to fit on there is 7.4. And I have 30 squares along the bottom. All right, so I need to figure out what to make each square worth so I can use up as much of the graph as possible. Okay, so my biggest number is 7.4, and I have 30 squares to do that with. All right, so I'm going to take 7.4, my biggest number, and divide it by 30. So it's saying that each square should be worth 0.2466667 centimeters. I should round that conveniently to what? 0.25. Okay? That makes sense, right? It's not much of a round. It's an up round, which we have to do, and it's an easy number to count by. All right. So every line's going to be worth 0.25. So to make my life easier and so that you can actually read my graph, I'm going to just go every fourth line is 1. Okay. So follow along. Do what I'm doing here. Oh, this is so much better. The marks are actually going where my pen is now. Okay, and this here, this last line, is 7.5. All right, so that fits perfectly. Okay, my last point is going to be like right at the edge of my graph. All right, what do I need to put at the top of this graph that I haven't done yet? Title. Okay. I'm going to call it my circles graph. Most of the time we write it's this versus that. I mean, we could say it's diameter versus circumference, but I'm just going to call it my circles graph. Okay. And I put diameter down here on the x-axis, but I didn't tell people that's what it was. So I need to put a label down there. It's diameter, and it's in centimeters. Yeah, centimeters. Now I have to prepare my y-axis. So the biggest number I've got to fit on my y-axis is 23.1. I have 37 lines on which to do that. Okay, so each line's supposed to be 0.62. That's not a great number to count by, okay? But I'm pretty sure I can count by 0.7, right? I'm just thinking if I'm counting by 7, it's like 7, 14, 21, 28, 35, 42, yeah. Okay, all right. So that's what we'll do, okay? We'll make each line worth 0.7 on here, okay? But again, I don't want to actually do each line because it'll be messy, all right? So I'm going to do every second line is 1.4. Okay, that's as far as I need to go. My biggest number was 23.1. I'm up to 23.8. Okay. I need to write that this is circumference. And it's in centimeters as well. Now I got to plot. Okay, simple as that. I got to put the points on my graph. Will I have to estimate some of them? Yep, I'm gonna. Okay, that's part of the reason why we draw a best fit line. We know the points themselves have a certain amount of plotting error, right? So my first one is at 1.8 and 5.6. All right, so this here is 1.75, so I'm gonna just follow it up. Okay, and I go to 5.6. Okay, which actually happens to be a line. So I'm gonna say that that point's right about there. Okay, that would be about right. My next one's at 2.8 and 8.9. All right, so okay, there's about where 2.8 is, and 8.9 is going to be right about here. Okay, 3.2 and 10.2. All right, so this line here is 3.25, so I'm going to be just inside of it. And I'm looking for 10.2, so that's going to be a little bit, probably right about there. Nope. It's probably a little bit high, but we'll go with it. All right, 4.4 and 13.8. Okay, so this line here is 4.5, so just inside of that, and 13.8, so that line's 14, so probably somewhere like that. 6.6 and 20.6. Somewhere around there. And 7.4 and 23.1. Now that line right there is exactly 23.1, so I'm going to say it's about there. Okay, so now I've got my best fit line, or sorry, my points. Now I need a best fit line. A best fit line does have to be drawn with a straight edge. All right, so if you don't have a ruler, you can use the side of your calculator, okay, or another sheet of paper, just set it beside, okay, draw it on there. All right. I have a little trick with mine because you can't put a ruler on a smart board, it doesn't work. Okay. So I'm going to say, where should I start my best fit line? If I'm looking at the relationship between diameter and circumference, if I have a diameter of 0, what's my circumference? 0, right? If you don't have a diameter, you don't have a circle. So I can start my best fit line at 0, 0, realistically. Can you always start your best fit line at 0, 0? No. Okay? Lots of times you're not going to be able to start your best fit line at 0, 0 because that wouldn't effectively follow your points. Right? We'll show you some examples of that later. But right, I'm going to start at 0, 0 because it's logical to do so. Okay? And I'm going to go, let's say something like that as my best fit line. Okay? Quite a few of the points are close to it. Okay, I think it might actually be just a hair steep, so I'm just going to bring it down a tad. Okay. Now I can find the slope of this line. Agreed? What should the slope of this line be? If I'm trying to find the relationship between diameter and circumference, what other number usually goes in there? .14, otherwise known as pi. Yeah, my slope of this line should be pi. The closest I have ever gotten is 3.138 when I draw this line. Okay, I was so close. All right, but that's what I should get for a slope. So I want you guys to draw a best fit line on your graph, okay, and then we'll see how close you can get to the actual value of pi. That's what we know it should be. It'll tell you how well you drew your line. Okay. So what I'm going to do is I'm going to use rise over run and y equals mx plus b both ways. Okay, I'll get the same number, but I'll just show them both as a calculation. So I'm going to find a couple of grid intersections. There's one right there. That's a good one to use. And here's one right here. So I'm going to use those two values. Okay, this will be point number 1, and this will be point number 2. So y2 is 21. Y1 is 7.7. X1 is 2.5. And X2 is 6.75. All right, so now I can do slope equals rise over run. Okay, and so that's going to be, for this one here, y2 minus y1 over x2 minus x1, and that's 21 minus 7.7 over 6.75 minus 2.5. Okay, so we're looking at what, 13.3 on the top, okay, and 4.25. Oh, I'm liking my chances here. Okay, on the bottom. All right, so we had 21 minus 7.7, okay, divided by 6.75 minus 2.5. Okay, that's pretty darn close. All right, 3.129 is not half bad if my actual value was supposed to be 3.14. You know what that means? When I said that line looks a tad steep, I screwed it up. If I'd have left it where it was, I probably would have got exactly 3.14. All right, but such is life. This is still pretty close. Okay, it means I drew my best fit line pretty well. All right, everybody with me on that one? Okay. How many people got, let's say, between 3.0 and 3.3 for a slope? How many people haven't calculated the slope yet? Okay, draw your best fit line and calculate your slope. I'll give you a minute. Okay, then I'm going to resurvey. Now, the other day, we did this problem, this v equals d over t problem, where we said that if you looked away from the road while driving for 2 seconds, okay, how much distance you would miss while you looked away. Okay, if you recall, at 100 kilometers an hour, that was over 50 meters. All right. So I said I was going to do this little test, and then we never did it. So I'm going to use Taylor here as my guinea pig for this. Okay. I'm going to show you the difference in reaction time between when you're paying attention and when you're using your phone. Okay. So Taylor's going to need to take out her phone. Okay. So first, though, I don't want you to use your phone. I want you to put your hand at the edge of the desk so that you're you'd be able to grab the ruler, because I'm just going to drop it. Yep, yeah, just put it, there you go. Okay, so pay really close attention. When I drop the ruler, grab it. Okay, so it fell, she grabbed it at about the 24 centimeter mark. Okay, so it fell 24 centimeters before she grabbed it. Okay, and that was when she was paying attention. All right, now take out your phone and just start doing something on it with your hand ready there. Okay, she caught that on the rebound after it hit the floor. Okay, that's what usually happens. Okay, she caught it a quarter of the way down the last time. This time it fell the whole length of the ruler, bounced and came back up before she caught it. It fell 5 times farther when she wasn't paying attention. Okay? It could take you up to 5 times as long to react to something if you were not paying attention. Okay? That's a long way in a moving vehicle. And that's just a simple test. Okay? Every one of you would have performed the same. Okay? It's just human nature. If you are not paying attention, you miss things. Okay? The whole ruler drops. So don't feel bad, Taylor. It happens to everybody. Okay? Yesterday, when I did this with my period 2 class, was the first time someone caught this before it hit the ground. Okay? It was the first time, and I've been doing this now for like 10 years. Okay? It was the first time somebody caught it before it hit the ground. They caught it like here. Okay? It was like at the 95 centimeter mark. Okay? They just barely caught the ruler. All right? Everyone with me there? Lesson to be learned here? Don't be stupid. Your phone is not something you should have in front of you while operating a motor vehicle. Okay? I mean, geez, they put stuff on pills. Don't take this pill and operate a motor vehicle. They should write that right on the front of your phone. Do not operate this while using a motor vehicle. Okay? Yeah, you're more dangerous than a drunk when you're texting. Okay? Realistically.